Hello students, I'm back with you. We're now going to continue with the next part. I think that's part 3 now, yes? Part 3 of chapter 2. Okay, and we'll be looking at instantaneous velocity and instantaneous speed. Okay, right. Now, just to go back a bit quickly, we spoke about average distance. There it is, average speed. That's your average speed, distance over time. And average velocity will be your displacement over time. Okay, now what is instantaneous velocity? And remember here, for average velocity, we picked 2 points on the graph and we drew a straight line between them and we found the gradient of that line. That's the average gradient or the average velocity between those 2 points on the graph. Okay, so here they say instantaneous velocity is defined by this. Now you can see here, that is same as for average velocity, delta x over delta t, but we have something else here as you would have done in calculus at school, the limit of the average velocity as delta t tends to 0. Right, as delta t tends to 0, and you know from school calculus also, we could have written the same thing as dx by dt. In other words, extremely small changes, delta t tends to 0. Right, and remember this here, as we know, is also a gradient. The limit effectively is a gradient of a graph. Okay, so what is this gradient? From schoolwork, you should know that this dx by dt, or the instantaneous velocity, that should actually be, as we will see now, the gradient of the tangent at a particular point on the graph. So let's look at the graph quickly. We have 3 scenarios here. The first one is the one that we had. Say there we have pi and pf. Pi is this point. Pf is that point over there. Then you draw a line between them, and then you find the gradient, right? Vertical change divided by horizontal change. So that will be your, this here would be your delta, let's call it delta x, and this here would be the delta t, that one over there. If I were to make my delta t smaller, right, can you see here? This is my first delta t. Now my delta t is that amount, delta t1. In other words, I move this thing a bit more. So I've got that point over there now. If we call P final 1, right? So we now need to find average velocity for that, or we find gradient for that one. So it must be the gradient of that line, right? Your delta t is smaller, right? Okay, so the gradient between pi and pf1 will be the gradient of this line. And then you go take it further, make your delta t even smaller, smaller, until your pf, can you see pf means your final point, right? And pi is your initial point. So your pf is on p1. In other words, my delta t is now equal to 0, right? And that means now that we are finding the gradient of this green line. And this is a line that is a tangent to this curve, this black curve. This line is a tangent to the black curve at point pi. Right? Can you see there? The gradient between pi and pf. That is because pf is pf2, sorry. If pf2 lies on top of pi, then we are actually working out the instantaneous velocity. So this line where you can see the 2 lines, 2 dots separately, that will be an average velocity. When you see these two, this line where you see the 2 dots pi and pf separately, that is an average velocity. But when pi and pf are on top of each other, then the line that represents, a straight line, is a line which is effectively the tangent to the graph at pi. And that is called your instantaneous velocity, right? Okay, people, you have done this thing in school when you spoke about the Newton quotient at school. And you people will be discussing, if you haven't already discussed this thing, in mathematics. I mean, I'm in first year as well. Okay, right. So the instantaneous velocity will be the gradient of the tangent to the graph at the particular point. Right. Okay, and what do we know? Instantaneous velocity is also a speed. And the instantaneous speed, what is instantaneous speed? It is the magnitude of its instantaneous velocity. Read that again. The instantaneous speed is the magnitude of its instantaneous velocity. Right, we're not going to get a graph like this for speed, okay, for distance necessarily. So when we're talking about the instantaneous speed, if you have worked out your instantaneous velocity, remember this will be positive or negative, or this way or that way, your direction. So we just take the magnitude of that, and that can be called the instantaneous speed as well. Okay, so that is speaking about instantaneous velocity. It is still a gradient, but remember the gradient of the tangent at a particular point on the graph. So if I were to have a line, say for example here, if I at the maximum point over there, what's the gradient over there? It will actually be a horizontal line. Then it means instantaneous velocity at that moment is 0. Then if I go there, to that point over there, then you have a straight line going through there, the tangent there. Then that will be the instantaneous velocity at that point. Okay, always a tangent to the graph. Okay, so what do they say here? Okay, that is that discussion, and then we have to continue to speak about constant velocity as well. Before we do that, there are two examples that they want us to look at in the textbook. So let's go back to the textbook, example 2.2 and example 2.3. Let's go back there and see where we are on example 2.2 and example 2.3. There we are. Example 2.2, and there's example 2.3 immediately. So what do they say? There seems to be a bit of a discussion problem. So what do they say? They consider the following one-dimensional motions. Number A, number B, and number C. What does A say? A ball thrown directly upwards. It rises to its highest point and falls back during its motion into the thrower's hand. The next one, a race car starts from rest. From rest means 0 speed, from rest, and speeds up to 100 meters per second. Okay, and case C, a spacecraft drifts through space at a constant one straight line, obviously. And the question is, are there any points in the motion of these objects at which the instantaneous velocity has the same value as the average velocity over the entire motion? Right, you take the average velocity over the entire motion, initial point and final point. Is there any point where the instantaneous velocity is equal to that? Okay, so in case A, what do they say there? A ball is thrown directly upwards, rises to the highest point, and falls back into the thrower's hand. So if you want to take the average velocity, what will that be? Remember, your initial position was in the hand, and the final position was back in the hand. So the total displacement was actually 0. And if you take the time divided by the time, your average velocity is 0. So is there any point in this motion where the instantaneous velocity is also 0? Remember, we move up and you come back down to the same position, right? So the initial position and the final position is actually the same. People, this is actually a straight line up and down. I'm just drawing it like that for us to see. So there's no displacement that way. The displacement, vertical displacement, is actually 0. So displacement over time from there to there will give you an answer of 0, and that means your average velocity is 0. And we know as this thing moves up, it slows down, slows down, slows down. So the instantaneous velocity decreases until it reaches that point, and then it decreases to 0, and it continues, and then it increases again there. And there, the instantaneous velocity is 0 at the maximum point. Right, so that would have been discussed in the solution over here. Okay, next one. We have a race car. It starts from rest and speeds up to 100 meters per second. How did they say, how is this thing traveling in a straight line? Speed, they don't say. Is it the average speed or is it average velocity? They're not saying, they actually just say speed up. So this is not very clear, this particular case over here. Starts at rest, so initial speed is 0. Final speed is 100 meters per second. So the average speed, if you take that as velocity, then that will be, actually we didn't do this formula. This particular formula, we didn't discuss that. But you don't know what the nature of the travel was of this person. So it's not really clear what one can actually see. There might be or there might not be something there. Right? I think this number B actually discusses it like that. And number C. Number C, a spacecraft drifts through space at a constant velocity. So remember, the constant velocity means the velocity remains the same. Right? And that means the instantaneous velocity will be the same value everywhere, isn't it? It will be the same value everywhere. And what will the average velocity be? Effectively, what did they say here? I'm just trying to think what did they say? Let me just, I'm trying to work out what they say, what they read. Yeah, I'm a bit yamaka now, but confused. Because the spacecraft's instantaneous velocity is constant, it's the same everywhere. Its instantaneous velocity at any time and its average velocity over every time will be the same. Okay, I'm just trying to think in terms of velocity and acceleration now. Yeah, if your velocity stays the same, then your average velocity will be the same, and your instantaneous velocity will be the same as well. That is for case C. Yes, right. Okay, so that's example 2.2, a bit of a discussion problem. Right, can you see the kind of question they ask, right? And you must be prepared to answer questions like this as well. Right, not just calculations, you must be able to interpret them as well. Okay, right, number 2.3, average and instantaneous velocity. And what do they say here? A particle moves along the x-axis here, right? That's the x-axis. So it moves along the x-axis. Its position varies with time, and that's why as time continues, it pans out this brown graph. Okay. So let's say its position varies with time according to the expression here, that expression. Notice here, this is actually a parabola graph. Can you see here? You remember, for a parabola, you would have said y is equal to ax squared plus bx plus c. Right, that is a formula for a parabola. Can you see the x squared and x and no x? X to the 0, x to the 2, x to the 1, and x to the 0. And if you look at this one over here, can you see it? That's here, we don't have x here, but we have a t, right? So the x will be y over there, and the t will be the x. So, and there you can see t squared, x squared, and 1t over there. There we are. And this term is actually 0, right? We can call that the y-intercept also, right? So that will be the x-intercept. That is 0. So there you can see, and starting there at 0, And notice, why is this a parabola? You can see it's a parabola shape. How do we know the parabola is going that way? The value of A. Look at this value of A. If you remember, if this is a positive value, then you have a parabola that looks like that. If this is a negative value, then the parabola looks like that inverted one, right? Okay, and here you can see, according to this formula, positive 2. Right? So that is why we actually have a parabola that looks like that. Right, people? That is just going back to what we have discussed in terms of graphs at school already, right? And I'm sure your mathematics lecturer will be speaking about that as well. Just keep these two in mind, this shape and that shape. So that is for a negative value here, and this is for a positive value there, the t-squared portion, right? Okay. Okay, where x is in meters and t is in seconds. Time graph, they given because the position of the particle is given by a mathematical function. The motion of the particle is known at all times. Remember what we said right at the beginning? If you know the position at all times, then that is how we can speak about motion, right? So there we are. Okay, the formula tells us at any moment in time what the position of the particle is. Okay, that's obviously the way it is here, from there to there, but actually according to the formula, right up to infinity. Okay, now let's continue. Unlike that of the car that we spoke about earlier, right? Where we use the table to get the data. Now notice that the particle moves in the negative direction initially for the first second of motion. You see, in the negative direction, right? So it moves down, right? It moves opposite, right? If I were to draw a graph from there to there, it moves from 0 to -2. So it moves in the negative direction for the first second, and then here it turns around and it moves forward again, right? Going back to the origin, back to the reference point, and going further towards positive. Okay. We see that? Okay. Where is it momentarily at rest? Where is it momentarily at rest? At this point over there. How do we know it's at rest? Remember, the gradient of this graph is horizontal here at that point over there. So that means the velocity at that point, at 1 second, the velocity there is 0. All right. That's why they say at rest, at t equal to 1 second. Okay. What's the question? Determine the displacement of the particle in the time intervals from there to there, from 0 seconds to 1 second. Find the displacement. What's the displacement? That's my initial position, 0. That's my final position, -2. Right. So effectively, final position -2 minus initial position, 0. And that should give me an answer of -2 meters. Let's see if they have it like that here in the solution. I didn't even look at the solution now. There it is. You see that? Okay. Right. And then what is next? And there's another one there, from 1 to 3 seconds. What is your what you call it, from 1 to 3 seconds? So look at the graph. You have to look at the values on the graph, right? So your initial position is 1 second, the initial time, and the final time is 3 seconds. Now where is that? So maybe the initial value is -2, and the final value there, according to this graph. Let me just see quickly up. Sun is in my eyes. It looks like, according to this, it will be 6, right? Would you agree with me? At 3, the graph goes to 6. You can confirm that if you want. I'm looking at the graph But if you want to confirm that at 3 seconds the position is at 6, this position formula, and then you put 3 in here. So it's 4 times 3 and 2 times 3 squared. So that is 9, 18. Right? That is 18, and that would be minus, what do you say, 3 times 18 minus 12 is 6. Yes, that's correct. So that is 6. Okay, so x final is 6 and x initial is minus 2. Right, so I'll just do it here. It's again, it is 6 minus, and here we see, as we discussed earlier, minus 2. Right, you must keep the minus of that position there. Right, 6 minus minus 2, that means 6 plus 2, and the answer is 8 meters. Okay, let's see quickly. There we are, 8 meters. You can see it's positive also, right? Okay, so that's the first question. Then there is another question they ask us to do here. Oh, see, there's B and there is C. What is B? Calculate the average velocity during these 2 time intervals. So for the first one and for the second one. All right, so the first case here, there's the average velocity is displacement over time. So there's your displacement over time. That was over 1 second, right? So minus 2 over 1. So the velocity, average velocity will be minus 2 meters per second. Am I right? There we are. And for the second one, 8 divided by, what's the difference? It's from 1 to 3. So it's 3 minus 1 is 2, 2 seconds, right? So that will be 8 divided by 2 is 4, positive 4 meters per second. There we are. And then the next question, find the instantaneous velocity of the particle at 2.5 seconds. Now, students, instantaneous velocity. Instantaneous velocity. What do we do here? Here you'll see what they did here. Right? I'm not going to do it like this. All right? Okay. Here they explain to you what they did and to get the instantaneous velocity. Right? Okay. Let me just check the slope of the green line. Where's the slope of the green line? This green line over there. Right? So if you have, they say at 2.5 seconds, right? Here at 2.5, you get that line over there, and then you have to draw that, then you find the slope of that line, right? Now, if you are going to do this, how do you know that this slope is accurately drawn? I'm not absolutely certain, right? I suppose according to these people, it will be according to the textbook writers. They can say that this was accurately drawn, and they can work out the vertical distance over the horizontal distance to get that slope, and that will be your instantaneous velocity. Right, but we will do it. I'm going to do it a different way now. Now watch me now, and now note, students, please take this thing down because it is not as part of the notes. Right, this example is not in the notes. Remember, the formula says that the instantaneous velocity is also like the Vx, that is equal to dx by dt. Now, I assume that you people have done differentiation at school, right? You've done differentiation at school, so you should be able to differentiate this graph, right? Where's x? X, I'm going to write it somewhere here. X is equal to, what was the answer? I can't remember now. No, let's just go back to the problem statement. It is x is equal to minus 4t plus 2t squared. Okay, there you are. Minus 4t plus 2t squared. Now remember, if you differentiate now with respect to time, and then this portion, remember that is t to the 1. So that will be, if you differentiate this term, it will be minus 4 times t to the 0, so which means it's minus 4. And then this one over here, it will be 2, it's a plus there, right? Yeah, plus 2 times That will be, if we need to differentiate this here, that will become, I assume that you remember your differentiation from school, if you haven't done it at campus yet. So that will be 2 times 2t. That 2 comes to the side, right? Times t to the 1. Right? 2 times 2t. So what do we have here? That is equal to minus 4 plus 4t. Okay, so that's the derivative of that there. The derivative of this over here will be given by this. And now we can say they asked for the question at 2.5 seconds. So all that we need to do now is we need to substitute 2.5 into your time. And then what do we get? That will be equal to minus 4 plus 4 times 2.5. 4 times 2.5 is 10. 10 minus 4 is equal to 6. What is the answer there? See that? 6 meters per second. Okay, so that's another way in which you can find your instantaneous velocity. Right. Okay. Right. Okay. Right, so those are the examples they wanted us to do. Let's go back to the notes, the 2.2 and 2.3, and then we can continue to that discussion on constant velocity. I think what I'll do is I'll do this now because it's not a long section that I want to discuss before I continue with this. Right, I'll continue with the next lesson. Yeah, so let's continue with constant velocity as well. What do we mean by constant velocity motion? Okay, they say here, consider now the case when the velocity is constant in time. That means v remains the same for all time. So this will be depicted therefore on a graph as a horizontal line on a velocity time graph. Can you see there? If you have velocity versus time, velocity versus time graph, not a position versus time graph, a velocity versus time graph, then you can see the velocity is constant. That's a constant velocity. Okay, now remember, on a position time graph, velocity is the gradient. So the gradient of this line, the gradient of the line is your velocity. So according to this then, a velocity versus time graph, a constant velocity will be horizontal. So on a position versus time graph, the constant velocity must therefore be shown as a constant gradient. In other words, that line does not change. Okay, can you remember this one over here? If you had a position versus time graph, can you see that line and the green line? All of them have different gradients, different slopes. So this is definitely not a constant velocity graph, right? This is a changing velocity graph, right? Because the gradient of the position time graph changes. Now on this one over here, if you have a constant velocity, then on the position versus time graph, the velocity remains the same. So here I've shown you this one over here. Why is this one corresponding to that one? The reason is you can see here the velocity. If this is 0 over here, then the velocity is a positive value. You see that? So therefore my gradient here must be a positive gradient. Can you see? Remember, that direction is a positive gradient and that direction is a negative, less than 0, a negative gradient, and that is a positive gradient. You can see that line, a constant positive gradient, one straight line. If I were to have something like this here, I'll just show you quickly. It should be straight lines. That's a velocity, Vx, and there's your time, and I have a velocity there. That should be a V. It doesn't look like a V. Let's do it over again. Vx. What do we see here? If that is your 0, then this is a negative velocity. Right? This is a negative constant velocity. So how will we show that on the displacement versus time graph? That's x. You must always indicate your labels, right? Displacement versus time. How will we show that on here? You can actually see it must be shown as a negative gradient here. So it will be like that, right? A negative gradient. So this here on the velocity time graph shows a negative gradient on the displacement time graph. And a positive constant velocity shows a positive constant gradient on the displacement time graph or a position time graph. I'm still used to saying displacement time graph because that is how I normally taught this thing at a school when I was teaching physical science at school. I always called it a displacement time graph, but the correct way really is to call it a position time graph because this thing effectively just tells you your positions. Okay, all right, so there we are. Here they have another example for us to go through. Example, I thought it will be done, but okay, let's have a look at example 2.4. Oh, yes, before we do that, let's have a look at here. I see they gave us a formula. Where did this formula come from? If you were to look at this one over here, x final and x initial, and then you have a time t, assuming we start from 0, right? Assuming, right? Remember here, the formula for average velocity would have been x average velocity, right? I'll just do it here, f vx, okay, average velocity, but that's also instantaneous velocity. Now, I had in that previous example, 2.2, your instantaneous velocity and your average velocity will be the same if you have a constant velocity. Right, that will be x final minus x initial divided by t final minus t initial. But if you assume for the moment here that your initial time is 0, then your t final can just be called t. Right. So if you want to change, make x, f the subject of the formula, you can see, take that over there, multiply it to the vx, and then you have to take that over the minus x, so that will be on the other side, will be a plus. You can see the xi plus vx vt. So this one is a way for you to find your displacement, your final position. Your final position will be your initial position plus vxt. So remember, this is true for this formula. You can put a block around it to remember that. You can must try to remember that, because I don't think these formulae will always be made available to you. That is for constant. Well, okay, that formula is true for constant velocity. Okay, so let's have a look here quickly. See example 2.4. Let's go back to the textbook. Constant velocity, right? Okay, now is example 2.4. Please, you can read through the textbook as well, right? To just check that you understand those things. What do they say here? A kinesiologist, don't ask me what that means. You can go check up in Google what that means. Oh, there they say. A kinesiologist is studying the biomechanics of a human body. It has something to do, some biologists, I suppose. I assume so, right? Oh, here they say it's a study of the movement of the human body. Okay, there we are. Kine for motion, right? Kinesiology is a study of the movement of the human body. Okay, I didn't know that. Okay. Oh, there is a kinematics, movement. So kinesiology has to do with the movement of, in this case, the human body. Okay. Now, she determines the velocity of an experimental subject that is a human being obviously, while he runs along a straight line at a constant rate. Constant rate, that means, here you can use constant rate. Remember, rate means, in this case, displacement divided by time, right? In other words, a constant speed in a straight line, so that will also be constant velocity. The kinesiologist starts the stopwatch at the moment the runner passes a given point and stops it after the runner has passed another point 20 meters away. Okay, so the runner has been running, so passing point I, initial, she starts the stopwatch and stops it when the point passes the other point. Okay, the time interval indicated on the stopwatch was 4 seconds. So that 20 meters was covered within 4 seconds. What is the runner's velocity? Right, constant velocity. So we can therefore say the final position and the initial position. Right, 20 minus 0 divided by your 4. Right, and that will give you your 5. Okay. Can you understand? Just have a look at this one. This is interesting. Look at the way they gave the information. 4.0, so that's 2 significant figures. I'm looking at the significant figures issue. 20 meters, right? And this is from rest is 0, right? Okay. But remember, we just say rest, so that is actually an infinite amount of significant figures. Why? Because that is a number that's counted from rest. Are you with me? You didn't measure that initial position. You just said that that is the initial position, so you gave it a counting number. So that has an infinite number of significant figures, but that's important. Just 20 minus 0 gave you an answer of 20 according to subtraction rule. So you get 20 over 4.0. So it is 2 significant figures divided by 2 significant figures. So my answer, now 20 divided by 4 is 5. But I can't write 5. I have to write it to 2 significant figures. That's why we said 5.0. See, if you were to write 5 here, I'll mark you down. Right, I'll mark you down. Okay, well, you don't lose all the marks, but I'll definitely deduct a full mark for that. So please, your significant figures, right? Very important. Okay, number B. If the runner continues his motion after the stopwatch is stopped, what is his position after 10 seconds? That means we're making the assumption that people running at the same speed, right? Okay, what is his position after 10 seconds have passed? Right, now remember his initial position was 0. So what is his final position after 10 seconds? So now we can make use of that form. Plus this. Now we worked out the velocity, right? So we can use that velocity there and multiply it by your time. Okay, let's see. Okay. That's a 5 multiplied by 10, and that is equal to 50 meters. And again, you can see there 2 significant figures, 2 significant figures, and the answer is given in 2 significant figures. Okay, so there we are. All right. Please remember this formula, right? This formula you people would not have discussed at school, I assume. But you can see here, because we are talking about position and not displacement. Right. Okay. We speak about position. That's why we can use this formula. Right. Thank you. Okay, students, I'm going to stop there and continue with this section in the next discussion. Thank you. Bye.